Well, welcome to Paris, everybody. My name is Marc, or most will know me under Van Hauser from PhD. Been around for 15 years, 17, 18 years or something, so seen all this stuff, which is pretty nice because with IPv6 it's like, oh, seen that 15 years ago already, so things come up again and again. Yeah, I'm doing IPv6 since 2004 actually, so even before there was even really IPv6 available. But here this is now new stuff. So, who has already heard my previous talk I did in 2005? That's pretty good. Maybe who saw my talk at CCC Congress in December? Okay, if you want to leave, it's already 3 new slides or something, so other than the entertainment factor, there will not be that many news. Who played with IPv6 so far? Because my feeling is for most it's still kind of like science fiction Star Trek or so. Okay. Please raise higher because my dear side, I'm an old man. Okay. Yeah, still not so many. I mean, come on, you're hackers. There's still so much to hack. I tell my stories later. Who has IPv6 at home or at university, company, whatsoever? Yeah, that's not really much. Okay. This will change until next year. Promise. Okay, as I said, IPv6 is for most people something like, oh, this will never ever happen. Yeah, it's like, yeah, sure, IPv6, but the truth is that we all have IPv6 already among us. On all the operating systems you're running, you have IPv6 enabled by default. Except if you run FreeBSD, then you're outdated. But everyone else has IPv6 enabled already. Hi. So, the question is, if it's already there, what can we do with that? And I did lots of research in that area 5 years ago, and yeah. But let's start with the basics because I only saw very few hands. I would have done the slides anyway. So. IPv4 address, you all know that, pretty easy. 4 octets, 4 billion possible IPv4 addresses. Yeah. Looks a lot, but we know it's not enough. IPv6 that has 16 octets, has so many possible IPv6 addresses, I have no idea on how to pronounce that, but it's enough. Plenty. And this is how an IPv6 address looks like. So instead there are dots, there are colons, and there's kind of hexadecimal. So how is such an address created? 2 bytes, so 2 octets are converted to hexadecimal. They're separated by colons. If there's a leading 0, these can be omitted. So this would be 0004 or 20B3, for example. And the longest chain of 0 colons, so 0 colons, 0 colons, 0 colons, can be replaced by a double colon. That's way how you can make them look smaller and easier to write down. So this is what you will type in the future when you try to SSH into some machine. Yeah, long IPv6 ago. Try to remember them. Subnets, and this is now really a big change. They are /64. I mean, the whole internet was /32, yeah? But now every subnet is /64. How this is 4 billion times the whole internet. That's just one subnet. I mean, what do you think how many systems could be in a subnet? How does this make sense? It makes sense when we talk about auto configuration later. That's why the subnets are that large. There are no broadcasts left. There are multicasts, but multicasts are only locally for you. Because it's always the same address. Wherever you are, the multicast addresses are always the same. That's why you can't access multicast address from a different network. And it has lots of features. You have auto configuration, which is, I think it's the coolest feature. It's like DHCP, but it's in the protocol, so it's done with ICMP version 6. So plug and play everywhere. Get routers and everything. You have IPsec. You have mobility, which is also very interesting. Let's say idea. So I'm here, I have my SSH session open to some server, I get on the train, then I fly, let's say, to New York, and I can have my SSH sessions open the whole time active, with my same IPv6 address, while I'm mobile in the world. And we have, of course, enough addresses. at least for another 5 years. So this is how an IPv6 header looks like. And if you know IPv4, and I hope everybody knows IPv4 here, otherwise it might be kind of the wrong conference for you. This is how it looks like, and it looks pretty simple compared to IPv4. And now the big question is, what has changed to IPv4 besides, of course, the address sizes? So hands up. Who can see the difference to the IPv4 header?
Checksum.
There's no checksum, that's correct.
There's no IP ID.
There is no IP ID field anymore, that's true. Yeah, that's a low-level cluster. They changed a lot of names because of, yeah, it's cool protocol to change names and people have to learn new stuff. Like hop limit. Hop limit is time to live. Yeah?
Okay.
They just renamed all the fields. Yeah, they killed fragmentation. How's that possible? There's no fragmentation anymore. So, let's see the list. There is no header length anymore. Well, because in IPv4, there are header options. And that's why you had to put in the header, that's the header size. Now the header size is fixed, it's always 40 bytes. So we don't need the header length field anymore. There is no identification field, which was because they noticed it makes no sense. It was an interesting idea, but it was never used. No use whatsoever, so they removed it from the protocol. There is no checksum because it's all done in the upper layer. Even ICP version 6 has now checksumming. There is no fragmentation anymore, which of course only half the truth. It's not there here. And there's no options with all, again, only half of the truth. So, it looks pretty simple. If something is simple, it's easy to analyze, it's easy to secure, it's easy to implement, so things should be fine. But now there comes something new in there, that's extension headers. Everything which is not in the basic IPv6 header becomes an extension header. There we have fragmentation again. There we have source routing. There we have, what, source routing? Yeah, it's back again. IPsec. We have destination options, we have hop-by-hop options, and a few other things we can skip at the moment. So we have lots of extension headers. So how does this work with extension headers? You have an IPv6 header, and let's say you want to do source routing with your packets. You have another header, which is the routing header. That header points to the next header, which could be fragmentation. Then you have the next header, which is UDP, and then you have the data. Yeah? So in theory, it looks way, way simpler in IPv4. Yeah? Because if you just have the IPv6 header and then UDP header, it's very simple. But let me ask you a question. What happens if I first put the fragment header and then the routing header? Or what happens if I have the IPv6 header, then a fragmentation header, then a fragmentation header, another fragmentation header, and then let's say hop-by-hop option header? What happens then? Or what happens if I do 200 hop-by-hop extension headers in a row? Nobody really knows. And that's where the complexity comes in. So in theory, it's simpler. In reality, it's very, very, very complex. So even that is just the start of IPv6 becoming complex. And it's so complex that the designers themselves have no clue really how IPv6 really works. Yeah, I can rant on and on about, for example, when they designed IPv6 said, oh, DHCP is bad, why? Everything should be in the protocol, so who needs DHCP? Okay, so what did they do? We put that in the protocol, say DHCP is obsolete. Okay, they did that and everything's fine until someone noticed, well, what about the DNS server? Do we need a DNS server in auto configuration? Because it's not in there yet. So who needs a DNS server when network connectivity? Oh, fuck yeah, we forgot that. That's how professional they are. Then I say, okay, oh, we could use DHCP for that so they get the DNS server, which of course is not the point. So only I think last year they put out an RFC that they finally also announced a DNS server in the router advertising. That's how the auto configuration works. Yeah. But it wouldn't be these nice, very knowledgeable people if they didn't come up with just 3 ideas on how to do that, how to solve only that problem. So it's not only, there are 2 more options how you can distribute the DNS server information, yeah? Because it's better to you have more options so every vendor can guess which could be the best. So if you're Windows, if you're Linux, you might have different features you support and they're not working with each other. So lots of stuff which goes wrong in IPv6. Now skip that now. Yeah, IPv6 vulnerabilities. Yeah, You see, it's getting more and more and more. 2011 has just started, and already 5 vulnerabilities have been announced. And if you have submitted CVEs and stuff, and you know how releasing advisories work, you find a vulnerability, you submit it to the vendor, you wait half a year for a reply, and another year more for the final release, and then you can maybe update your advisory and send it out. Well, so this means also 2010 is already gone. There will still be advisors being released with CVE numbers from 2010. For example, I myself have still two open for 2010. And these are not counting my own CVE entries, which are still open. And I have quite some, because it's really easy to find something. Yeah, so my expectation, because of the number here, we have 5 in just 1/4 of a year. So multiplied by 4 would be 20, would be here, but I would guess there will be even more. Yeah. So as we can see, IPv6 is so easy to implement, it's so hard to implement that it's very easy to make mistakes. So in 2005, kids, I did my first presentation on IPv6 insecurities. And it was really just the very, very, very basic stuff. And what was really the news about it was that people get informed, okay, these are the issues, and finally there's the tool to exploit that. So that was basically what it was about. So I created the THC IPv6 attack toolkit, a toolkit which has all the things you need to attack IPv6. I had to write my own package library. It was really a pain in the ass because the libnet and all the tools didn't have an IPv6 support yet, so that's why I had to do my own. So just to wrap that up very quickly, because it was already in the old slides, and you can look it up or look the video on YouTube. There's ARP spoofing, but it's not ARP spoofing anymore. Now it's called neighbor discovery spoofing, because it's not done by ARP anymore, but it's done with ICMP. But the mechanism is exactly the same. You have a neighbor solicitation, so you do the ARP request. Who has this IPv6 address? And you have a system which has this IPv6 address, then answers with a neighbor announcement or neighbor advertisement saying, yeah, this is my IPv6 address. But of course, anybody can answer to those multicast requests and say, yeah, that's my IPv6 address, and do the spoofing. And for that, there's a tool, Parasite 6. Duplicate address detection does returns, of course, in IPv6. It's even more important than on IPv4, actually. Also works with neighbor solicitation, so if nobody answers to your ARP request, yeah, you know this IP address is not being used. But if somebody answers, then you can't take it because there would be collision. So that's what this tool is doing, looking for those requests and then saying, yeah, I have that IPv6 address, I have that IPv6 address, I have that IPv6 address, and yeah. The systems can't join the network. Then there is man in the middle with redirects. So ICMP redirects return, of course, to IPv6. I'll skip away on how this mechanism works, but this mechanism works in a way that even if you enable secure redirects, you can still redirect the traffic to you. So secure redirect is not secure. Secure redirect is like labeling, yeah? Oh, secure here, but it's not really. It works with IPv4 the same. Yeah? So even on IPv4 ICP redirect, secure redirects is so easy to bypass, it's not really worth anything. Then we have DHCP, which is in IPv6. Of course, you have DHCP version 6, which is kind of similar, just more complicated, but I'll skip that here. We have the auto configuration feature. Auto configuration works in a way that a router sends a router advertisement to the network, and that router advertisement has information. It tells everyone on the network, I'm a router. These are the routes I'm advertising, and if you want an IPv6 address, this is the network space to choose your IPv6 address from. This is how it works. So, but anybody can tell the network, I'm a router too.